the title is a mouthful, but I'll be covering each of these terms as we go on. But before that, a bit about me. So as Evan said, I just started my PhD a month ago. I'm supervised by Dr. Chirag, who's here. And previously I worked at Shell, where my role was forecasting power from wind turbines using graphs. So we'll talk a bit about human understanding, and I'll begin by showing you 3 images. And just a quick few seconds before I show you the next 3. And I think your brain has immediately made a bunch of connections between what are similar images and what are dissimilar based on content and other features. I don't even need to show you these lines, but you can still figure out what these animals sort of are without knowing their actual names. This goes to show that humans are quite good at generalizing, and we can generalize from very few samples. You can read this paper, they actually discuss this in great depth, but this is the gist of it. And we sort of want machines to do the same for us. We want them to be sample efficient and learn quickly. The reason we want to do that is sometimes you don't often have enough data, such as cancer classification in the medical domain, or you need a lot of money. So only OpenAI can do things. And to close this gap, we have few-shot learning, and specifically, I'll be focusing on few-shot classification. And when I say generalization, I mean generalization within the context of few-shot classification, so not AGI. And I'll be talking now a bit about the standard setting of few-shot classification. The reason this is important is going forward, we'll be doing this in an unsupervised manner, which is what my work deals with. But it's important to understand what happens in the standard setting as well. So in a standard few-shot setting, you're given n classes with k examples per class. So that means if you have 2 classes of cats and otters and 3 examples each, you end up with 6 images. And your labeled set is called the support set. This is what the model learns from. And in an unsupervised setting, as we'll see later, we do not have access to the labels. So not only do we need to learn from a support set, we also need to evaluate how well the learning was. And that's why we have our query images, which are unlabeled, but the classes remain the same. So the classes that you see in your support set are also present in your query set. You just have more samples that you're expected to classify, and your model will be evaluated on these sets. Yeah. But together, the support set and the query set constitute as what we call a task, and each task is a mini classification problem in and of itself. So you learn from the support, classify on the query. But it's important to keep in mind that the actual test time classes are not the same as your training classes. So the distribution is almost entirely different. There's some overlap, but they're significantly different. So to do this in an unsupervised manner, we need to induce this notion of similarity in the network. It needs to understand which images are similar to each other and which are dissimilar, without necessarily focusing too much on the actual animal itself. So if we take this cat and transform it twice, and we represent this in your representation space using a convolutional neural network, we want the representations, which are just vectors, to be as similar as possible for all 3 images. And these transformations, by the way, are called augmentations. You can do a number of them, but you need to ensure that the representations are the same. So just a visual for the same, if I have the cat, the original one, and Ollie, who lives in my building, and you project them in your representation space, you bring their augmentations and the source images close together, and that's a good thing. But you don't want the cats themselves being pushed apart from each other. You ideally want these guys to be well clustered together in a representation space. But since they're not doing so in a standard contrastive learning setting, we have to come up with a solution for it. And the solution is titled SAM transfer, where the name of this presentation also comes from. And what is SAM or SAM transfer? So it's a combination of a pre-training and a fine-tuning method. So the reason pre-training comes in is because this is meant for the unsupervised setting. And fine-tuning because at test time we get tasks as I described earlier. SAMP stands for self-attention based message passing, which is the graph component of this. We use graphs to refine the representations from a convolutional encoder. And finally, this is to help the network exploit relations between representations. So I personally believe that graphs can be used to approximate the human model of the world. We often keep concepts of the world in our mind and not necessarily every detail about the concept. At the same time, we also have relationships between these concepts that we exploit. If we can bring a semblance of this into our network, we can also induce the notion of similarity and dissimilarity and help it classify images. So in my network architecture that I'm using for SAM transfer, there is a convolutional encoder in the beginning. And there is a message passing there that uses self-attention for the actual refinement of the features. In this case, we have the two original cats and also an otter. Of course, we want our cats to be together in the representation space, but the otter should be a bit far away. And earlier we saw that the two cats were being pushed apart. And in this case, we do a better job. I'll show you visuals later, how this translates to actual data. But yes, our cats do end up together and the otter is a bit away from them, which is what we expect. And this is what we need for classification.
But these nodes are the representations of this cats, right?
Yeah, sorry, yes. So the nodes that you see are just vector representations from the convolutional network.
What edges represent it?
Uh,
Dependencies for or something?
So the edges are attention weights. So these are learned. They're not exactly learned, but they are produced from the data itself. So I'm not initializing this graph as you would normally do. So this graph usually ends up with in a fully connected form. And then the attention weights decide if every connection is as important as not or not.
These attentions are then in some sense learned, right? So do we
Yeah.
win?
Yeah. So we didn't do the actual classification itself. And for the classification at the test time, we first aggregate the support samples in the representation space to form prototypes. And prototypes are just an aggregated version of the supports which represent a certain class. In this case, it's a prototypical otter or a kitten. And you just have to measure the Euclidean distance between these prototypes and you're unable to query samples. And then you can classify them to be of one type or the other. So it's a pretty simple linear classifier and it gets the job done. But there was another problem here that we noticed. It's not directly related to graphs, but I think it could be useful. We saw that in the representation space due to the distribution shift at this time. The support samples were sort of clumped up together. And they were no longer representative of the class they were supposed to represent. So as you can see, there's an imaginary decision boundary. There's a cross on the orange side supposed to be a kitten, but it's being classified as an otter. And that's simply because the prototype happens to be closer. So the way to fix this, and one of the simplest ways to fix this, is through optimal transport. With optimal transport, we're trying to project these support samples onto the query samples. So we treat them as two different domains. And this is in an attempt to increase the spread of the prototypes so that you increase the spread of the support samples, sorry, which leads to a more representative prototype and you can get better classifications out of this. And this only works if your learned encoder was already good enough. And these are some numbers. I won't go into too much detail here. But the gist of it is that we perform quite well with a very small 4-layer convolutional network on two important data sets, namely mini ImageNet and tiered ImageNet. In some cases, our method also comes close to supervised methods. And as promised, here are some visions during the pre-training. So on the left-hand side, you see features that are pulled out of the convolutional encoder. You can see in some places that the dots are a bit spread apart. But the moment you pass them through the message passing layer, they are in a lot of areas, they're tightly grouped together, which is what you want. But this does not necessarily mean that it would translate to your evaluation phase. So for that, I have a simpler example here. So the test time task here was a two-way classification where the support set had 5 samples for each class and 15 queries in total. So as you can see on the left, again, it's convolutional features. You see some of these orange dots in the sea of green, and it can be extremely hard to classify in such a scenario. But the moment you go to your message passing layer, refine your features, you can see that the nonlinear decision boundary becomes a bit more easier to classify or learn. So to recap, we spoke a bit about few-shot learning, and specifically my method, which is using unsupervised pre-training for few-shot learning, and a little bit about prototypical classification as well. So if you have any questions, now is the time.